Thank you, Mark, for your nice introduction. And as Mark said, many thanks to all of you for being here today so early after all the wine and good food that we had yesterday evening. Much appreciated. And of course, many thanks to Alberto for inviting me and for putting together this excellent symposium in this excellent location. So as you heard, my name is Emilio Martínez-Pañeda. I'm an associate professor, UK senior lecturer in mechanics and materials at Imperial College London. And today I want to present a new theory, a new model based on phase field and electro-chemo-mechanics that we have developed to predict the evolution of voids and current hotspots in all solid-state batteries. And this is work that I've done together with my PhD student, Runzi Wang, and together with my former Cambridge colleague, Ying Zhao, who's now a professor at Ying University. And we published most of what I'm about to present in a recent JMPS paper, so you can find additional details there. I think the good thing about presenting on the last day of the symposium is that I don't need to spend a lot of time on the motivation. We already had a good number of excellent talks on the area of solid state batteries. So this is an exciting area that is attracting a lot of attention because, well, solid state batteries could be the next big disruption in battery technology. The ambition is to replace the liquid electrolyte by a solid electrolyte, and that should enable the use of lithium metal as anode material, which can increase capacity by roughly an order of magnitude. However, mechanical instabilities at the lithium metal solid electrolyte interface are hindering the uptake, the viability, the commercialization of these solid state batteries. And so there's a lot of exciting mechanics phenomena happening here, a lot of exciting and puzzling mechanics phenomena. And particularly problematic are these dendrites, so these needle-like filaments that originate at the interface between the lithium metal anode and the ceramic electrolyte, and that propagate all the way into reaching the cathode and causing the short circuit of the battery, so the cell death and the short circuit of the battery. So there's an interest on trying to understand how those dendrites grow. You can see some dendrites nucleating and growing here. You can see that they go all the way into causing the short circuit of the battery, the cell death. And these dendrites seem kind of unstoppable in a way. So once they originate, once they form, once they nucleate, they don't seem to arrest. They go all the way to reaching the cathode. So we thought that in our first attempt to come up with these modeling efforts, we should put the focus on trying to predict and understand how those dendrites, under which conditions those dendrites nucleate. And what we know from experimental observations is that those dendrites, the formation of those dendrites is related to the evolution of voids in the lithium metal anode and the associated local current hotspots in the electrolyte. So let me elaborate on that a little bit with this nice microscopy images from Peter's Bruce group in Oxford and some sketches that I've done below. So initially you have an almost pristine interface between the lithium metal anode and the ceramic electrolyte. But then every time you discharge, you have stripping, that is, you are removing lithium, and therefore you're generating those voids that you see there. And every time you have plating, every time you charge, you have plating, that means that you're depositing lithium, and therefore you are making those voids smaller, and eventually you're even isolating those voids. So you're creating this kind of occluded voids that are isolated from the interface. And understanding this voiding process is critical because whenever you have those voids, as you can see here, you generate this current hotspots, these localized regions and the electrolyte near the edges of those voids where the current accumulates, where you have high localized current density. And in these regions of hotspots of high localized current density, you have an exacerbation of plating, and this additional plating leads to the propagation of those dendrites that go on to cause the short circuit and the cell death. So we need to understand how those dendrites evolve to be able to predict. Essentially, we need to minimize voiding and we need to minimize current hotspots if we want to minimize dendrite nucleation and growth. And one of the key hypotheses in the community is that the most effective way of minimizing those dendrites is by, or minimizing those voids and those current hotspots, is by applying a constant mechanical pressure on top of the anode, so a stack pressure. And therefore, then the voiding process becomes a competition between the rate at which lithium is being replenished, at which is being dissolved at the interface, which scales with the stripping current density, and then the rate at which lithium is being replenished, which is related to the lithium diffusion and also the creep effects that you get from that stack pressure. And trying to predict this competition is complicated because you need to capture how voids of arbitrary morphology evolve. Those voids can merge with other voids, they can divide. At the same time, you need to capture this over multiple charge and discharge cycles, and you need to capture that together with all the electro-chemo-mechanical phenomena that are happening, that are governing how those voids evolve and how those hotspots are being created and those dendrites and so on. So I think it's quite complicated from a computational perspective. And in fact, I'm not aware of any model that is able to do that. So this is what we try to do. And we try to come up with a modeling framework with a theory and a modeling framework that will allow us to predict how those voids would evolve and all the electrochemomechanical phenomena that is happening in there. And we soon realized, of course, that there's many analogies that we could draw with other things that we have done in other areas, right? Because we've been modeling electrochemomechanical problems in many other areas like corrosion or hydrogen embrittlement and so on. And we have also, more importantly, we have also seen that now we have computational tools that allows us to simulate the evolution of complex interfaces. And this tools is this so-called phase field method that you heard about already in the symposium. And the idea is quite simple, but computationally quite compelling. So instead of having the interface between two phases, describing that interface as a sharp, discontinuous interface, you can smear that interface over a finite domain and then use an auxiliary variable, this phase field variable, to interpolate between the two phases. So this auxiliary variable, this phase variable, will take a value of 0, a distinct value in each of the phases, so a value of 0 in the blue phase, that is the voided region, for example, and then it will take a value of 1 in the red phase, that could be the lithium metal, the solid lithium metal phase 3. And then it will vary smoothly in between. And then just by defining a differential equation for the evolution of this phase field, you're able to capture complex morphological problems, interfacial morphology problems. And there's multiple advantages to it. 3 that I like to list as usual is that one is that the interface equation is defined in the entire domain, so there's no need for any special treatment. A second one is that topological changes, such as divisions of merging of interfaces, can be naturally captured. So you can capture how those voids will merge or divide without any ad hoc criteria. And then the third one is that the interface equation can be easily combined with equations describing other physical phenomena. So it's a method that is very well suited for multiphysics problems. And in fact, phase field methods have been a revolution in many areas of science and engineering. For example, microstructural evolution, fracture mechanics, and also corrosion. We have recently seen that can also open new horizons in the modeling of corrosion. And I should also say that, I mean, you can see here how very complex interfaces can be captured, right? You can see multiple cracks initiating, growing, and so on. So it's quite a compelling computational tool in that regard. And we have used phase field to simulate the evolution of cracks in battery materials before. Specifically working with, in collaboration with Paul Shearing's group at UCL, we have simulated the evolution of cracks at the particle level and also at the electrode level, as nicely presented by Paul on Monday and by Adam through a poster yesterday. And more recently, together with my friends at Imperial, Billy Wu, and the postdoc that we could supervise, Wei Long, we have also extended this framework to fatigue to be able to capture on both idealized particles and realistic 3D particles the evolution of cracks. So we're trying to combine, in both cases, multiphysics modeling, phase field fracture, and this kind of advanced imaging. And I mean, a number of people have been using phase field to model the evolution of cracks in particles, starting by the pioneering work of Bob McMeekin. But I believe that we are the first one to extend it to the case of fatigue because they were mostly focused on modeling 1/2 cycle. But this is, of course, a cyclic damage process. And I think it was important to extend it to fatigue. And we are also seeing yesterday and the day before that phase field can also be used to model the evolution of dendrites within the electrolyte. So it is, I think you would all agree with me that it's a suitable tool for capturing interface evolution, morphological evolution of interfaces within multiphysics problems. But let me take you back to our problem and describe what I think are the key physics that we need to incorporate into our model. So there's many things happening here. One thing, as we already discussed, is the interface reaction. So we need to capture the fact that whenever we have stripping, we have lithium that is being removed from the lithium metal anode and going into the electrolyte. And whenever we have plating, whenever we have discharging of the battery, then we have lithium that is being deposited on this lithium metal anode. So that is one key element that you need to capture, this interface reactions. Another aspect that you need to capture is the vacancy diffusion. So the substitutional surface and bulk diffusion that you have here by which lithium will be attracted to the interface during plating, during stripping, and then moving away during plating. A third aspect that I already discussed is the voiding, which is essentially a consequence of the nucleation and annihilation of vacancies. So during stripping, you'll have vacancies being annihilating and those voids being created. And during plating, you have those vacancies being nucleated and those voids being closed and eventually becoming occluded from the interface. And then last but not least are the mechanics effects. And this is mostly lattice distortion due to the lithium transport, the vacancy diffusion, but more importantly, the creep effects that you get when you apply this constant mechanical pressure, this stack pressure on top of the board. So let me explain you how we choose to model each of these phenomena. And for the sake of time, I'm only going to focus on the theory. I'm not going to get into the details of the numerical implementation, but I'll be happy to discuss those during the Q&A session. So let me tell you first what are the primary fields. I'm going to start focusing on the anode only. So the anode basically has two regions. There's the voided region, and then there's also the solid phase region. And within the solid phase region, we can talk about the lithium transport, the lithium occupancy. So we can discuss that. We can assume that the lattice sites are going to be either occupied or vacant. And if we do so, then we can define a lithium concentration, several concentration measurements, and a lithium occupancy, which is going to be our primary field for the transport problem. Then if we're trying to model the void evolution, then here what we have is the phase field, which describes this evolution of voids due to this annihilation, nucleation of vacancies. And therefore, what you have is this phase field auxiliary variable or order parameter that will be 0 inside of the voids. It will be 1 outside of the voids, and they will be interpolated with this interpolation function h in between. So of course, inside of the metal, you have no, inside of the void, you have no strain energy density, you have no concentration, but in the lithium metal, all those quantities become relevant again, and you interpolate them with those interpolation function. And then in regards to the mechanical behavior, I'm going to use the displacement field as the primary field, but I just want to say that there are 3 components that go with the strains. So you have elastic strains, then you also have chemical strains due to lattice distortion, and then you have this viscoplastic behavior of lithium, which we capture by means of an ANS model. And if you put all these fields together, you can easily define the Gibbs and the Helmholtz free energies, and you can derive the associated chemical potentials. And then from those, you can, of course, obtain the balance equation, the strong form of the balance equation of your problem, the balance equations of your problem. And here you can see the example for lithium transport. And I think 2 things that I want to emphasize here is that the model naturally captures the enhanced diffusion that you should see in the surfaces. And this is done through this term here, because the gradient of the hydrostatic stress will be strong along the void surface. And I think something that is a bit more interesting is that through the boundary conditions of this transport problem, you can capture those interface reactions, that lithium deposition and dissolution that you get when you do plating and stripping. And this is captured through this flux boundary condition that is dependent on this local current density that you have in there. And so we'll change sign whenever you have plating and stripping. In regards to the governing equation for the phase field, you can see here is kind of a Canhilliard type of phase field equation. And as I said before, it reproduces this nucleation and annihilation of vacancies that leads to those void formation and evolution. And then in regards to the mechanical load is the standard balance of linear momentum, where of course you have this interpolation function with the phase field because the voids do not have any stiffness, cannot carry any load. And a boundary condition that we're gonna explore is application of that constant mechanical pressure, that's stack pressure on the edge of the anode. In regards to the constitutive behavior, we take an ANS viscoplastic model to model the viscoplastic behavior of lithium metal, and we fit the parameters of the model to be able to reproduce the experiments by Lepage and co-workers at different strain rates. And last but not least, we not only model a chemomechanical problem, we also want to solve an electrical problem. So we want to couple this description of the anode with the electrolyte. We're also solving for the electrolyte, which we assume to be an elastic solid. It's a ceramic electrolyte. And we solve their Ohm's law in both the electrode and the electrolyte. And one important thing and of course we ensure continuity of current and potential along the interface. And one important thing is that we capture the fact that we interpolate the conductivity of the electrode. And this is quite important, of course, because this is one that's going to create the host hotspots, right? The fact that you have this abrupt change from the conductivity in the lithium metal to the void. And this abrupt change is going to lead to those current hotspots. So before I show you some representative results of the model, let me summarize what are the key elements of the model. So First, we model this vacancy diffusion, the substitutional lithium diffusion, bulk and surface diffusion by means of this transport equation, where the primary field is this lithium occupancy in the lithium metal anode. We model the lithium dissolution and deposition through the interface boundary condition, through this flux boundary condition as a function of the local current. We use the phase field to model the annihilation and nucleation of vacancies, so the voiding process itself. You can see here the phase field evolution equation. And regarding the viscoplastic behavior, this is done through creep by using an ANS model. And last but not least, we are also interested in simulating the electrolyte, of course. So we look into the electrolyte, and particularly important is that we define the conductivity of the anode to be dependent on whether you're in the void or the solid region, and that leads to the current hotspots. So let me show you some representative results. This is a simple boundary value problem where you have a void in the middle, you have a lithium metal here, and then you have a classic LLSZO electrolyte on the right. And yeah, you can see here superimposed equations that we're solving in each domain. And here you can see some results for stripping. So what I'm showing here on the left, these contours here are the phase field contours. So the phase field is blue, 0 inside of the void, and is red equal to 1 in the solid metal phase. And then what I'm showing here on the right is the normalized current. So this is the local contours of the current density. And you can see basically that you get what you expect from the experiment, right? So you're having stripping, so your void is growing mostly along the interface. And then you see that you generate those current hotspots, those localized regions of high current near the void edges. And yeah, you can see it here. That again, as you see in those experiments of Peter Bruce, you see how as you do stripping, you see how the void evolves and mostly along the interface, and how you get this localized current there, which eventually is going to lead to the nucleation of dendrite. Regarding plating, you can see the results here. Again, phase field on the left, normalized current on the right, and you can see essentially the same qualitative features that we saw in the experiment. So as you deposit lithium, you are closing the void, those current hotspots eventually disappear. And if you plate for a sufficiently long time, you even see what you see in the experiment, this kind of isolation or occluded voids that separate themselves from the interface. And yeah, again, you can see it here, that eventually you do get that kind of void occlusion that you see in the experiment as well. And of course, then we can change parameters in the model and try to see if we get the qualitative behavior that we expect to see from the experiments. For example, we can change the applied current, and as you would expect from the experiments, the higher the applied current, the higher the rate at which the shape of the morphology of the void changes for both stripping and plating. You can also use the model to try to understand the interplay between creep and diffusion and see which one has a higher contribution relative to the other. And this is something that has been discussed widely in the experiments. And of course, you can use the model to capture any kind of realistic scenario, right? I was showing results for a simple boundary value problem, but you can capture behavior of multiple voids over multiple charge and discharge cycles, and any arbitrary, I would say, initial distribution of voids or pressure or charging conditions. So let me show you some results with a more realistic case where you have multiple voids, you're applying a pressure or not applying a pressure. We will see both the scenarios, and again, solving those that coupled electro-chemo-mechanical problem. And you can see here in the absence of pressure, multiple cycles of charge and discharge, and you can see how the voids grow and shrink, so to say. You can see here the evolution of the interface after multiple cycles. You can see here the influence of pressure. So you can see here what happens when you start. This is in the case of no pressure. And here you can see what happens when you apply a pressure of 0.5 megapascals. You eventually get some sort of void coalescence in there. So the model can capture naturally this kind of interaction between multiple voids. You can see here for the case of 1 megapascal, where you can see that actually you're getting some of the voids are actually disappearing from the interface. So this is kind of what you expect from the experiments. And you can see here some pictures of those videos. So in the absence of pressure, and here what you can see the hotspots formed there, and here upon the application of a pressure of 0.5 megapascals, you can see phenomena such as void coalescence, which have made these hotspots disappear, for example. And here you can see for applied pressure of 1 megapascal, where some of the voids are being banished there. And this is basically how, as far as we got for our GMPS paper. And now what we're trying to do is to get a bit more quantitative. So this was our first attempt in developing a theory, a computational framework. But I think that has all the ingredients in place, and it seems to agree qualitatively what we see in experiments. So what we're trying to do now is to try to make it more quantitative and to not only be able to reproduce quantitatively the experiments, but also try to explore what happens when you change certain parameters like the charging conditions, or when you change the cell design, or when you change the materials that you're using. And one of the things that we've done is to implement the battle-warmer interface kinetics before we just assume continuity of current and solve for the overpotential here. And then, yeah, again, add multiple voids and see what happens. And one of the things that you can see is, of course, that you can measure the potential polarization. So you can apply a current and measure the voltage over multiple cycles of charge and discharge. And you can see how you get this potential polarization, this increase in voltage that you see in the experiments as I would say, the surface integrity becomes more and more degraded. Either you have many voids or you have multiple voids that are growing and interacting with each other. And this is essentially kind of qualitatively what you see in the experiments as we have discussed, and some of you have shown yesterday. So let me just conclude, hopefully in time for a few questions. Excellent. So I just want to say that our goal was to develop a phase field-based framework that combines this phase field paradigm to be able to capture arbitrary evolution of that morphology, those voids, with an electro-chemo-mechanical model, kind of mechanistic electro-chemo-mechanical model that describes at the continuum level all the atomistic phenomena that are happening during this process. And I think that the model does a good job in being able to predict the void evolution and the hotspots, at least qualitatively. And we can capture those as a function of both pressure, material, and charging conditions, both magnitude and also loading history. We can do this for multiple loading cycles. We try to make the model as mechanistic as possible, trying to incorporate all these phenomena that we think are governing this process, so the annihilation and nucleation of vacancies, the substitutional lithium diffusion, the creep and the lattice distortion and so on, and the reactions happening at the interface. And that allows us to capture the interplay between this bulk and surface diffusion, the lithium dissolution deposition, the creep, and the vacancy nucleation and annihilation. So we can see what is the relevant weight of each of these phenomena. And then I hope to have convinced you that the model provides at the qualitative scale good agreement with experimental observations, so we can capture the void morphologies that we see in the experiments. We can capture the localized current hotspots that we suspected are happening in experiments that are leading to the nucleation of those dendrites. And we can capture this interplay between creep and diffusion and the role of applying the pressure and the applied current. So yeah, this is kind of our first attempt in modeling this exciting and complicated phenomena that is voiding and current hotspots and dendrites in solid state batteries. As I said, the focus has been on trying to predict and understand what are the conditions that lead to the nucleation and growth of these dendrites. And we have tried to do so by combining this mechanistic interpretation of the physical phenomena by developing a theory, a new computational framework. However, our plan now is to get more quantitative. So we want to be able to get quantitative agreement with experiments. That will be the next step. And this is where we're working now. And then, of course, the next step will be to start doing some sort of virtual testing, right? Once you get a quantitative agreement with experiment, you want to be able to change the anode geometry, the cell design, the charging conditions, map safe regimes of operation, and try to use this kind of virtual testing to try to assist in this solid state battery breakthrough. Thanks a lot for your time. Thanks.
Thank you very much, Emilio, for this interesting talk. We have quite some time for questions.